to trust it more? Can we assess how accurate results we obtain with it? So here is my email in case you would like to ask me questions after the conference is over. And let's proceed. Of course, we can use quantum chemistry to model almost everything which actually happens in reality. And you will see that the model, the approach we propose can be used to, I think, any physical model of any chemical process. But in this talk, I would like to focus on product ratios, because most chemical reactions are useful only if they produce the required product in a good yield and selectively. And what does it mean from quantum chemistry perspective? It means that the transition state leading to the main product should be well below the next lowest transition state leading to the alternative product. So there are many works in which scientists simulate transition states and calculate product ratios. And you can see, like in this very good paper by Stephen Wheeler, that there is quite a good correlation between the experimental and predicted enantiomeric excess. The enantiomeric excess is one of the ways to measure product ratio here. But when we obtain this one value, it's not enough usually to proceed and say that, okay, let's now synthesize this catalyst, because catalyst can be expensive, and you can waste many times and effort and money on making it. And you need to understand how much can you rely on your results. So one of the approaches which is used here by Wheeler is just to correlate experimental predictions with experimental values with predicted ones. And from here, he concludes that you can trust in predicted values by about 20%. They are usually about 20% off from the actual value. Let's see. I'm very sorry. I need to check where did that slide went out. It's here. Sorry. So this should have been the next slide.
Yes, came back.
Can you see? Okay, great. But this approach is only can only be used for rough calibration of our perception. From it, we see that indeed predicted values are within 20% from the experimental ones, but it doesn't hold for any molecule, so we can only use it here like a rough calibration, as I have already said. Another popular approach how scientists look at error propagation is considering errors coming from parameters of density functionals, basis sets, atomic positions. They sample close proximity of the optimal basis sets, density functionals, positions, and look how they affect their predictions. But this approach does not account for errors coming from all the other approximations, such as grid, salvation, everything else, which was not directly accounted for here. So from our perspective, the solution is to use a cumulative error in energy, which can be expected to be normally distributed, includes all sources of errors, and can be expected to have similar error bars for similar molecules, because mostly errors will be similar. Why the first is true? It's because of the central limit theorem, according to which normal distribution arises when there is a very big number of small independent error sources. On the previous slide, we have considered a very simple model with two transition states, but in real calculations, when we want to predict product ratio, we usually assess many transition states leading to each product, like you see here. And for this case, there is a extended formula where here goes summation over B over transition states going to B product at the top, and summation over transition states going to C product at the bottom. So how can we use errors in energies to assess our errors in predictions? Let's visualize how can it work using the Monte Carlo error propagation. First of all, this formula produces one value, one product ratio, based on all the transition state energies we have already found. So all this, for example, 5 energies of transition states produce one product ratio, read here. What we can do next? If we say that we know errors in transition states, we know the uncertainties in the transition state energies, then we can visualize these uncertainties with Weiland plots, and then we can sample all these uncertainties or these energy distributions randomly. We just sample one energy from this distribution, one from here, one from here, here, and use them in this formula and get this new value right here. Then we sample it again and again, and this way we obtain a new distribution, a distribution of the predicted product ratio, which is no more required to, and it's actually not normal distribution. It has a very complex form. And just for reference, this is the same approach which is used by the company 538 to predict outputs of the elections in the United States. This is a Monte Carlo error propagation. And it also can be used for molecules. However, here we still have one problem. We do not know how much uncertainty we have in these errors, in these energies. We do not know the width of these errors. So how can we obtain it? First of all, let me say that for normal distributions, we only need to know mean and the sigma, the standard deviation. And mu is clearly just the predicted, the computed energy of this transition state, because it's our best guess here, and we can expect the actual value to be distributed around it. However, when it comes to standard deviation, we can also find the connection with the mean absolute error, which is usually used to benchmark density functional methods, which is also called mean unsigned errors. And we can find some examples of mean absolute errors, for example, in this review by Trular, where the best functional has a mean absolute error of 2.16 kilocalories per mole, which is quite large from my perspective. However, at the same time, various other reports say that for transition states, mean absolute errors in their energy differences can be as small as 0.1 kilocalories per mole. So we require an additional approach to calculate these uncertainties. And here comes the second approach we have developed, Bayesian backpropagation. What is it about? We simply use the same approach as before, the Monte Carlo sampling, but we vary mean absolute errors. So, for example, we have here 5 transition states. We sample them with a mean absolute error of 0.1 kilocalories per mole, then with 0.5 kilocalories per mole, and so on, and obtain different distributions, which are shown with violin plots. Here we see that the larger the uncertainty in energies, obviously the larger the uncertainty in the prediction. And by the error of 1 kilocalories per mole, uncertainty in the prediction becomes that large that we actually didn't need to predict anything, just say there is some product ratio between 0 and 1. Luckily, our results show that usually the mean absolute errors are much smaller. But how can we choose the correct mean absolute error? We need to look at the experiment. I'm sorry, it's in Russian, but it says experiment. And then we look at these violin plots and the distributions and calculate how much each of these distributions overlap with the experimental value. For example, in experiment, we have an uncertainty of 2%. Then we can calculate integrals of this coincidence and the distribution which has the largest overlap between experimental prediction and the between the experiment and the predicted distribution will be the most likely one, and it's called maximum likelihood distribution. So from this analysis, we can say that in this case, mean absolute error of 0.5 kilocalories per mole has the maximum likelihood. Next, to look at how this works for actual reactions, we have used the Wheeler's data from this article. He has studied such reactions and obtained, as I have already shown, this trend. So we can use his experimental values and his predicted and his calculated energies to find out the maximum likelihood values of mean absolute error for different simulation models he has used. And here we obtain the a very interesting picture. which shows that this approach can also be used for benchmarking of quantum chemical methods. Here, all three methods are differ only in salvation model. The red one does not have a salvation model at all, and the blue and green one have salvation models, very similar ones, SMD and PCM. And here we have the plots of Maya likelihood versus Maya. So we can say that energies calculated with SMD B97D have the maximum likelihood of having 0.3 kilocalories per mole maximum average error, and mean absolute error. And PCM B97D have the maximum likelihood of having 0.35 kilocalories per mole of mean absolute error. These values are very close, and you can also note that these distributions of likelihoods are quite tall and not wide, thin. And when we consider the same function but without solvent model, we obtain a much larger mean absolute error, about 1 kilocalories per mole, and it has it's much more wide. So we can even say that we not only know that here the errors is larger, we have less information about which error here is actually in this case. We are less certain about the certainty of this method comparing to these two ones. So here we can come at three semi-conclusions. First, there is now an approach for force propagation of errors in total energies, and also an approach for back propagation of errors in of experimental errors into errors in energy. Prior to studying never seen systems and reactions, you can assess accuracy of your model on similar system or reaction with no experimental property value to estimate uncertainty in the predicted value. Here, I would like to stress that the approach we are developing cannot be expected to work to produce one value for all reactions and anything else, even when using the same level of theory. So it would be a good idea to check accuracy of your model, which incorporates level of theory, mechanism, the chemical model, of course, including salvation and other and all other approximations in your reaction or your in your process, chemical process or physical process you're interested in, so that you could use the uncertainty which is most relevant for your case. And finally, since I understand that many of the participants of this conference are working on their own quantum chemistry packages, I would like to note that our present results show that the salvation model is very important in modeling, at least in modeling chemical reactions proceeding in polar solvents. So their implementation, testing, and application in real life for real life problems can be considered necessary from our results. And I would like to show you an example of application of our approach, which is one of the which happened back when this approach was not here yet, was not developed, and has shown to me that this approach should be developed. So here, our colleagues from Germany contacted us and asked to model this reaction. This is a black rearrangement. Here it's written stage 1 and here it's stage 2. So the reaction takes this large catalyst. It attacks the substrate at this carbon atom and forms this intermediate. And then the anion produced from the substrate attacks the intermediate, but not with its oxygen, but with its carbon. Here you can see. And product is formed which has its stereochemistry, while the substrate doesn't have any stereochemistry. And all the stereochemistry in this product comes from the stereochemistry of the catalyst. We have modeled this reaction and located 4 transition states which are overlapped here, which correspond to the stereodetermining step, the step which determines the stereochemistry of this reaction. And quite unexpectedly, we have found that the main product should have R configuration, while according to the experiment to circular diachorism, the main product should have S configuration. And here, no, not yet. And here, if we assume up these contributions of transition state, we should get something about 50% R, while the observed one was 70% S. And at the time, we did not have any way to prove that we are certain about our results. So I have spent a lot of time trying to find additional transition states, calculating with different levels of theory and so on. But I could not do anything. I have arrived at the same contributions as here. And so finally, our colleagues have decided to make a crystal to study and study it. But before we go further, I would like to show you that these Weyl plots, which are constructed using our force propagation approach, can be integrated from 0 to -100. That is, we are estimating the probability of error of our prediction in the main product configuration. Here it is. And we can see that with the mean absolute error of 0.1 kilocalories per mole, we only have 0.1% probability of being wrong, which quite small probability. And at 0.25, the probability rises up to 10%, but it's still not that large. However, we can see that this prediction in particular is quite sensitive to the accuracy of our energies. Long story short, our colleagues have made XRD study and found that indeed the correct prediction came from the calculation. Actual antimetric excess was 70% toward R configuration. And S configuration from circular dichroism was a mistake, which came from a wrong annotation of the circular dichroism curves in the reference article, on which our colleagues have based their conclusions. The problem there was that the circular dichroism plot in supported information was different, had one assignment, and in the main part of the manuscript had the opposite assignment. And in the SI assignment was wrong. Here I think we can make one more conclusion. That is, if the observed experimental error is well above the expected one, then it's time to question the computational model, for example, mechanism, but also it's time to question the experimental interpretation. Because as our example shows, the experimental interpretation also can be wrong. And in our case, quantum chemistry has allowed us to correct the experiment, actually. So that's all I wanted to discuss today. Thank you for your attention.
Thank you. Thank you for interesting presentation. Just we again have one question, time for one question. Again, Anna Pomagay, want to ask, please.
Excuse me.